Hello, coming to you not quite live from One Take Studios, where today we have something fascinating called the natural base e. Yes, that is intentionally a lowercase e, and it is referred to as the natural base. That is its name. What is this? Well, there's a decent chance you're not going to like it just because humans tend to not like anything new and different, and this is definitely new and different. Did you know that e is a number? Kind of like pi. It's one of those numbers, decimals, goes on forever, never, no repeating pattern, nothing like that. In fact, if you were to look carefully at your calculator, I'll bet you find there's an E button on there someplace that you never even noticed. So what is this mysterious E? Where did it come from? Well, if we take this equation right here, we say, what is 1 plus 1 over n to the nth power? And let's take n and make it larger and larger and larger and larger. So what happens if we put a 2 for n? What happens if we put in a 10? What happens if we put in a 500 for n? As n becomes infinitely large, this gets closer and closer and closer to a specific number. What number would that be, do you ask? There, that one. E is approximately 2.7182818, and I know there kind of looks like maybe there's a pattern emerging there, but if you keep going, there's not. There's no pattern there. It just keeps going and going, again, like pi. Something definitely irrational. As far as where this comes from entirely, you might be looking at this going, hey, I've seen the compound interest formula for finances. This is very similar to that, and this is a take on that. What happens with the compound interest if we just keep increasing that number? Okay, so what do we do? Quite frankly, we do whatever we want to do. Everything that you've been doing with exponential stuff, with logarithmic stuff, all of it works the same, except we just have an e. So what if I wanted to graph? Because I could. This is an exponential graph, right? Exponential what is the question, though? Exponential what? We know that if the base, if the base is between 0 and 1, it's exponential decay, and if the base is bigger than 1, it's growth. 2.718, definitely bigger than 1. This would be an exponential growth graph, which should paint a picture in your mind, hopefully. We'll take a look at that picture here shortly. This is just another trip down memory lane, again, because this works with all kinds of things that we've seen before. These two guys indicate some sort of translation here going on as well. If I'm taking the entire outcome and elevating it by 1, that means all my y value is increasing by 1. That means that this graph is going up 1 unit. That's my k, if you think about h and k. Which means, what is that? That's my h. H is always affecting the x. It controls left-right movement. If it's a -2, well, if you think back to maybe some parabola stuff that you've done, even though it's minus, it means technically we're going to the right, and we're going to go to the right 2 places. So that is supposedly giving us an image that we might work with here. Let's take a look at what that actual image would be. Let's switch screens already here. All right, and there it is. My graph, e to the x minus 2 power. Yes, x minus 2 can be an exponent, plus 1. We can see, probably, that it's been elevated by 1, because there we go right there. Because typically exponential graphs have an asymptote where? Oh, that's right, the x-axis, and so this might now have an asymptote maybe at 1 instead, because that would be terribly logical. Everything goes up 1, including the asymptote right there. And this is supposed to have gone 2 to the right, but that's really hard to see. I pre-graphed, and I'm going to bring it back to light here. Give me this guy, give me this guy. Let's bring this into the picture, shall we? There we go. That is a little bit easier to see now. If we look at that, just e to the x, all right, so the parent function of that is in red. We can see where it would have an asymptote on the x-axis, and we can see with the blue that it has moved up 1 and it has moved 2 to the right of where it was. So all of our translation stuff, h and k, all of our transformations, all that kind of stuff still applies. It's just that we happen to have e as a number. What does this mean for domain and range? Let's think about that for a moment while we're here as well. Again, look at the blue graph, please. Domain is x, left, right. Is there anything to stop this thing from going left? No. Is there anything to stop this graph from going right? No. So my domain is going to be all real numbers. Can I say the same for range? Well, range of the y values, it's up and down. Will this graph go up forever and ever? Yes. Will this graph go down for... Oh, no, it can't go down forever and ever. How low does it go? Well, it gets pretty close to 1, And I bet you if you were to look at the table for this graph, it would tell you that it gets to 1. However, 1 is the asymptote. So this is going to get insanely close to 1, but it's not ever going to quite reach it. So what does that mean? Well, let's switch our screens back here for a second, shall we? Ta-dun-ta-dun. I said switch. There we go. All right, we said keeps going left, keeps going right, so x is a member of the set of all real numbers. That's our official, formal, scary-looking notation for domain. And what does that mean about range? Well, if the asymptote is at 1 and everything then has to stay above 1, I'm talking the y's that are greater than 1. Ta-da! There we go. So the y values such that y is greater than 1. The x values such that x is a member of the set of real numbers. All right, so, okay, graphing, great, whatever. Let's take a couple more trips down memory lane, shall we? What else can we do with this fun and exciting stuff? Well, let's give it a name here. Since e is the natural base, if I put e with logs, it becomes the natural logarithm. So just like a log without a base is the common log, base 10, a log with a base of e is called the natural logarithm because it uses the natural base. That means it also gets special notation that for some reason people's brains just hate. Log base e of x is not written as log base e. It's not a log. You write it as ln. Why it's ln for natural log instead of nl, I don't know. Feel free to Google that. But ln, I did a cursive L just so it doesn't look like a 1. Natural log of x means automatically it is a logarithm with base e. So if I see ln, this is what it means. If this hurts your head, then you need to rewrite it as log base e, because it works the same way. So that means we can do fun things like simplify. Ooh, other trips down memory lane. Let's see, what is this? What is this? Can we simplify this? Well, we see ln. That means automatically it has a base of e. There's my base of e sitting right there. Okay, so what can I do with this? Once upon a time we talked about, I see exponential form, I see logarithmic form together. Those forms are inverses of each other. So if I see an exponent with a base of e, and if I see a log with a base of e, these will undo each other. They are inverse operations, and what will be left is simply what is left. 0.15 t. That's a cursive t because I don't want it to look like a plus sign. And that would be it. That's as simple as you can get it. Ta-dun. Interesting. Crazy. But doable. That was so much fun. Let's do it again. Ooh, what is that? E to the. This whole thing is the exponent. 3 times the natural log of x plus 1. 3 times the natural log of x plus 1. That whole thing is the exponent for the e. Is it kind of like the last one? What do we see? I see an exponent with a base of e. I see a natural log, so that has a base of e. So that means I have both forms together with the same base. Can I just start canceling stuff? Maybe, if you think it through first. I have a 3 times a log. Find your properties of logarithms. What can we do with this? This is our swing property. I can take the 3 and I can swing it from being a coefficient up front of the log, and I can put it here instead as the exponent. So this becomes e to the natural log of x plus 1 cubed. Can I do that? Yep, I just did. There we go. Now I can see exponent base of e, log base of e, cancel each other out. These are inverse functions. They undo each other. What's left? X plus 1 cubed is what's left. That is the best I can do for simplifying. Again, strange, but true. Okay, let's try another one. What is that? Ew. Natural log of e to the 2x plus the natural log of e to the x. So maybe I go back to my properties of logarithms again and say, hey, I'm adding 2 logs. They're both natural logs, so they both have a base of e. How does that work? How can I add 2 logs together? I can combine them into 1 natural log, same base, 1 natural log. Why that one is, I don't even know. That's an L though. If I multiply, how do I do e to the 2x times e to the x? I might want to get out my properties of exponents. You notice how often we keep coming back to these guys? Might want to think that through a smidge, all right? So if I multiply, I keep the base, and I add the exponents. What's 2x plus x? That's 3x. So that is a combination usage of one of our properties of logarithms and one of our properties of exponents. But now, hey, now this is looking an awful lot like that first one that we were simplifying. It is a natural log, so it's got a base of e, and I've got something exponent with a base of e. So again, they will undo each other. 3x is my final answer on that thing. Ta-da! Alright, so everything that we've been doing, we can still keep doing. This e allows us to have a twist again on our compounding formula. If you have seen a compound interest formula, this is same thing taken to the next level. This is what if we could be compounding continuously, not once a year, not 12 times a year, not every single day, but constantly. What if we were always compounding our interest? That leads us to this delightful PERT formula. A, which is the final amount of our finances, equals P, which is the principal, the starting amount. So this would be the starting amount. This is the ending amount after time has passed. This is a money formula. E is E, again, 2.718. R is rate, and T is time. So I call it the PERT formula, principal, times e to the rate times time power. The r and t are both part of the exponents. So again, this is just another thing that we can do with this. This is not by itself anything crazy, but we can have it infiltrate all kinds of things that we've been doing. Please do not let it get the better of you, okay? Do not let it freak you out. It's just a number. It behaves like a number, except when it kind of behaves like a variable, but mostly it's a number. Okay? Have fun, enjoy, practice, don't freak out.